till now what we have discussed is there are two different kinds of forces. Okay, so forces were conservative and non-conservative, and what we understood is the conservative forces are the forces which do not depend upon the path. So so the work done by these forces is independent of path, right? What else did we discuss? So the work done is independent of path. There was one more thing. The work done gets stored as the potential energy. In general, I can say that whatever work we do in a conservative force field gets stored as a mechanical energy. Okay, could be kinetic, could be potential. So which is nothing but Ke plus Pe. So whatever work we are doing in a conservative force system does not get wasted, rather it gets stored as a mechanical energy. Whereas in case of non-conservative forces like air resistant friction, it would get dissipated in other unwanted forms of energies like thermal energy, noise energy, and others. Okay. We also understood that conservative forces are all the natural, generally all major natural forces are conservative. For example, gravity is conservative, and even the electrostatic force is conservative. And hence, since electrostatic force is conservative, the electrostatic force gives rise to electrostatic potential energy or the interaction energy. Now, when we talk about interaction energy or electrostatic potential energy, we start with a two charge system where we have a charge Q1 and we have a charge Q2 at infinity, and we are bringing it near Q1 at some finite distance r. And we understood that the electrostatic potential energy of the system is given by K Q1 Q2 over R. And eventually what we discussed is for a system of n charges, the electrostatic potential energy can be given by the expression 1 over 2 summation of I is equal to 1 to n summation of j is equal to 1 to n K Qi Qj over Rij. 1 over 2 because each pair we would be considering twice, and hence we have to divide by 2. So that is the summary. Now let's start with problems. Okay. So the first problem is we have a charge, positive charge of magnitude 7 microcoulomb, and we have the second charge of magnitude minus 6 microcoulomb, and they are at a distance of 70 centimeters from each other. A third charge is placed perpendicular to the system of two charges. Its magnitude is equal to 2 microcoulomb, and it is sitting at a distance of 40 centimeters. Okay. You're also told that the distance between the perpendicular point of intersection is equal to 30 centimeter here. You need to find the electrostatic potential energy or the interaction energy of the system. You can give it a try. Okay. So looking at this problem, see, there are two ways that we could solve. Either we go by the formula that we just discussed about system of n charges, where you have the summation, two summations and then k q I q j over r I j. Okay. Or we can go by the actual approach that we had discussed, where we would be constructing the system. Okay. One more thing to note here is that these values that are given to you are not in the SI units; it's in centimeter. So So we need to convert that. That is the first step, which people miss. So be very careful about that. Okay. So I'll go by the actual original approach. What we'll do is in bringing these two system of three charged particles, first we'll have to bring the first charged particle, right? So let's bring the first charged particle, which is Q1, and it is of magnitude 7 microcoulomb. Will I have to do any work here? No, because there's no external force being applied on this. So initial work done would be zero, right? Now I have to bring the second charged particle, which is Q2, and the magnitude is equal to minus 6 microcoulomb. And what is the distance between these two charges? It is 70 centimeter. 70 centimeter is nothing but zero point 0.7 meters, right? So I can write the work done in bringing the charge Q2 at 0.7 meters from Q1 as K Q2 Q1, or K Q1 Q2 over the distance, which is nothing but zero point 0.7. And this would be nothing but equal to the value of K into 7 microcoulomb. I should rather write this as 1 and 2, right? I think that would be confusing. So K Q1 Q2. So Q1 value is nothing but 7 microcoulomb and Q2 value is minus 6 microcoulomb over 0.7. If you remember the value of K from electrostatics chapter, it is nothing but, what is it? Yeah, so actual value is 8.99 into 10 raised to the power 9. So we approximate it to be 9, okay? Yeah, we can take that. We can do that approximation. And then what is the microcoulomb value? Very good. So 7 into 10 to the power minus 6 into minus 6 into 10 to the power minus 6 over 0.7. Okay. Now, if we do the approximation of 9 into 10 to the power 9, and then we make it 7 into 10 to the power minus 6 into 6 raised to the power 10 to the power minus 6 over 7 into 10 to the power minus 1. We can cancel 7 and 7. We can cancel minus 1 and it will become minus 5, right? And this becomes 9 6 54 into 10 raised to the power 9, and minus 5 and minus 6 will give us minus 11, right? Joules. So this becomes 54 into 10 raised to the power minus 2 joules, which is equal to 0.54 joules. Okay. So this is the work done when we bring charge Q2 near Q1. Now what we have to do is we have the main part of the questions. So we have to bring now Q3, and to do so we have to first calculate the distance. Okay, so let me go a bit down and we can do it here. So we have Q1 again here, we have Q2 here, and the distance between them was 0.7 meter, and then we have Q3 at a distance of 0.4, and this is 0.3. Now what we have to do is we have to first find this distance. So this is called as R13. Let's call this R13 and let's call this R23. So to be able to solve this problem, we need to first find what is R13 and R23 and then do the calculations, right? So what, and also you remember the principle of superposition. So we can consider them individually and then add them together, so we'll get the answer. What I'll do is I'll first calculate what is the electrostatic potential energy which is gained in the system when we are bringing Q3 in the influence of Q1 only. That, can you tell me what would be the expression? Yeah, so just tell me the expression. So K Q1 Q3 over by R13, right? R13 is the distance between Q1 and Q3. So the electrostatic potential energy gained when I'm bringing Q3 only under the influence of Q1 would be nothing but K times the product of the two charges divided by the separation between them. Now let's start putting in the values. So K is nothing but 9 into 10 raised per. What is the value of Q1? Let's go in SI. So Q1 was plus 7 microcoulomb. This was minus 6 microcoulomb. Yeah. And what do we divide by? What is R3? It would be 0.3 the whole square plus zero point 0.4 the whole square, right? We're applying the Pythagoras theorem. Okay, so this will yeah, but we're talking about the first part of the triangle. So this was zero point 0.3. Yeah, so Q1 and Q3. This would be 0.4. Yeah. So when we talk about Q2 and Q3, we'll consider 0.4. Okay. So what I'm trying to say here is that we are only considering this part of the triangle, this right angle triangle. Okay. So then this would become, I think, 0.3 square would be nothing but 0.9, and this would be nothing but 0.16. That becomes 0.25, and that would become 0.5, right? So we get 9 into 7 into 2 into 10 raised to the power minus 3, right? So minus 6 and minus 6 will become minus 12 and plus 9. So 9 and minus 12 will give minus 3, right? Over 0.5. When you solve this, this will become 5 over 10, and then eventually it will come out to be, I can do the math, so it will become 2 into 7 into 10 into 10 to the power minus 3 over 5, 9 to 18, and then you multiply by 7. When you divide this completely, it will come out to be, I think, 25 into 10 to the power minus 2. Did you get like this? So it becomes 0.25 joules. Okay. So we have found out the electrostatic potential energy between 1 and 2. We call this as U12. We also found out the electrostatic potential energy between 1 and 3. We call this 1, 3. Now what is left is between 2 and 3, right? So U2, 3. Let's do that. So we'll now be referring the second triangle, right angle, which you were saying initially, this one. So from directly we can say, right, because if so let's come down here. The second triangle is like this. We have 0.4 here, 0.4 here, and this is the actual distance. We have Q3 sitting here. We have Q1 here. Its value is minus 6 microcoulomb, and its value is 2 microcoulomb. So this distance, we can say, if the lengths of the base and height are equal, the hypotenuse becomes root 2 times the actual height, right? This is a short trick which you can, will help you. So I can simply write this as root 2.4. If you're in your exams, like competitive exams, you won't have time to do all the math. So you remember these things. So I can now write U, I think this was 2, right? So U23. Can you tell me the expression first? Exactly. So R23 we have to calculate, and we found out this would be equal to root 2 times 0.4. So let's put in the values. K is nothing but 9 into 10 to the power 9 approximately, and Q2 is equal to minus 6 into 10 to the power minus 6. Q3 is equal to 2 into 10 to the power minus 6, and we are dividing by root 2 times 0.4. When we do all the calculation, we'll get this to be 0.19 joules. You can check that for the benefit of time. Let's assume that this is the value. Okay. So now we got all the interaction energies, right? Individually. And we said, so we have got the interaction energy of all the pairs. So there were three charges and there were three pairs. One was Q1, Q3, we got U13. One was 1, 2, we got it as U12. And between Q2 and Q3, it was U23. We can say that the total uh, electrostatic potential energy or the interaction energy of the system could be given as 1 minute. All right. So we can say that the total electrostatic potential energy we can write as the sum of U1, U2, and U3, right? So I can write total U of the system is equal to U12 plus U23 and U13. And we know that U12 was nothing but we calculated it as 0.54 joules, right? So it would be equal to 0.54 plus 0.25 plus 0.19. And what is the sum? Sorry, this was minus 0.1 and I think I missed that. This would be minus, right? Because there is a negative charge there. Okay. So this would be the only negative thing. And the first one was also negative, right? 0.54 because there was also a negative charge here. Yeah, this would also be negative. So the first two U1, so this is minus 0.54 and this is also minus 0.19. There is only one positive which is between the Q2 and Q3. So quickly do the sum or the difference and let me know what is the value. Will it be 0.98? Can you recheck? So you think like this 0.25 minus 0.19, right? This will give you 0.06, isn't it? And plus 0.06 minus 0.54, what will it be? Minus 0.48, right? So yeah, be careful about the calculations, okay? Otherwise, the entire work done, which we do in the previous steps, will go to waste and you won't get marks. So in 12th board, calculations are very important, and step marking is there, but it's very subjective. Sometimes they do, sometimes they do not. Depends upon the examiner's mind. So you have to make sure that you are calculating everything till the end properly. Okay. All right. Now, can we make this a bit difficult, a bit more difficult? So we have already done. I'll just extend it a bit more. Okay. Uh, so we had the system of three charges. What I'll do is I'll just include one more charge. Okay. So this is the question two. Let's say it still depends upon question one. So you have Q1, you have Q2, and they are at a distance of 1 second. I think we can draw it neatly. So we have Q1 here, we have Q2 here, and we had Q3 here. And then we discussed that the distance between them could be given like this. We join it here. All right. Assume that this line is perpendicular, okay? And what I'm saying, the entire distance, the length of the line is 0. 0.7. So I'll make it simpler for you now. We are having 0.3 here. We're having 0.4 here. It was also 0.4. The magnitude of this charge was nothing but 7 microcoulomb. This was equal to 2 microcoulomb, and this was equal to minus 6 microcoulomb. Now what I'm doing is I'm placing a force charge Q4 here, and its value is equal to minus 4 microcoulomb. So we already have calculated the interaction energy of the system of these three charges, right? Q1, Q2, Q3. That would still be there. What I've just done is I've brought another charge and I am bringing it at a distance of 0.4 meters. And you need to tell me what would be the change in the interaction energy. So does it increase or decrease, and by how much? You just have to tell me the change. And okay. Okay. So let's solve this problem first. When we bring Q4, okay, as I just discussed, we will be having the force which would be exerted on us by Q1, Q3, and Q2, right? So all Q1, Q3, and Q2, all three of them would be exerting force on Q4. And because of that force, I would have to apply a force on Q4 also. And because of that, some work would be done on Q4 in bringing it till this point, okay? Because of that work, the interaction energy of the system would increase, or the electrostatic potential energy of the system would increase. Now, by principle of superposition, rather than considering all those forces applied all together, what we can do is we can consider individual forces and the work we are doing against those forces to bring it here. Okay. So those individual work done against those individual forces will give rise to individual electrostatic potential energy. So I'm calling this as 1,4, which would be equal to the electrostatic potential energy between Q4 and Q1. Okay. The expression for this is, can you please give me the expression? By, let's call it R14. So it would be equal to R14, right? And let's start putting in the values. So we have K as 9 into 10 to the power 9. We have Q1 as 7 into 10 to the power minus 6. And we have Q4 as minus 4 into 10 to the power minus 6, right? Divided by R14. So R14 is 0.4 and 0.3, right? This is a right angle triangle. So by Pythagoras theorem, it would be equal to 0.4 the whole square is 0.3 the whole square. We'll see what it is, okay? At least in numerator, what I can do is minus 6 and minus 6 will give me minus 12, right? So I'll write this as like 9 into 7 into minus 4 into 10 to the power minus 9, clubbing it together, into, sorry, plus 9 into 10 to the power minus 12. So I club the two 6 together, okay? In the denominator, 0.4 square will become 0.16, okay? Plus 0.3 square will become 0.09. Exactly. So eventually it will become 0.25, and then when we take a square root, it becomes 0.5. Perfect. And here we have 9 into 7 into minus 4. And we have this as 10 to the power minus 3. Now I can write this as, in the denominator it could become 5, and 10 to the power minus 1 will get cancelled. We'll get 10 to the power minus 2, right? And we can have a negative sign outside, and we have 9 into 7 into 4. Now it's up to you. What would you like to multiply? What I would do rather is, I know that 9 into 4 is 36. I'm just telling you how I will calculate. 9 for the 36 into 7 by 5, right? And into 10 to the power minus 2. Now, what you could do is either multiply and then divide. It's up to you. So So this would be again equal to 7.2 something, right? So let's do one thing. Let's multiply the numerator first. So 7 6 is 42. We'll get 4 here. 7 3 is 21 plus 4 will give me 252 by 5, right? Into 10 to the minus 2. And then when I divide this, we'll have 5 5 is 25.4, right? And there is 10 to the minus 2 also. So let's not cramp it here. So 252 divided by 5 gives me minus 50.4 into 10 to the minus 2, and that becomes minus 0.504 joules. Okay, so you can approximate this to be minus zero point 0.5 joules also. That is also okay. Okay, for all practical purposes. So we calculated U14. Okay, now let's calculate what is U24. So the U24, or let's call this distance as R24. Can you tell me what is the expression for R24, U24? And first tell me, what does U24 mean? Can you explain me what is U24? Again, you said force. Okay. Yeah. Okay. Okay. Can you tell me the story, Vidushi? What happens and how does the U24 comes? So first thing that we are sure about is when we are bringing Q4 near Q2, Q2 would be exerting some force on Q4, right? So force would always be there. That force would be given by Coulomb's force, K Q2 Q4 by R's, whatever the distance between them. We can call it as x square. That force is applied, and because of that force, by itself Q4 cannot come closer, right? So what you will do is you will exert some external force on Q4, which would be equal to the same magnitude as Q2 is applying, so that it can come to near Q2, right? And when you are doing that force, when you're applying that force and you're displacing Q4 from infinity, you are doing some work on Q4. That work gets stored as the potential energy. I'm trying to say it again and again so that you start remembering it. So because of the force applied on Q4 by Q2, it cannot come on its own from infinity. So you start applying some force which is equal to the same magnitude as what Q2 would be applying, so that it can slowly start coming here. And since it is moving by some distance and eventually it is coming at this distance, force applied over a distance gives rise to work. So you have done some work on this Q4. That works gets stored because this is a conservative force field and it does not get dissipated. And we are talking about that potential energy. So it is the electrostatic potential energy. Okay, give me the expression. Okay, now let's do this fast. So it's 9 into 10 to the power 9 into minus 6 into 10 to the power minus 6 into minus 4 into 10 to the power minus 6 divided by, it's root 2 into 0.4, right? Now we can write this minus 6 and plus 9 as 10 to the power minus 3 directly, and minus get cancelled. 6 4s are 24, so we get 24 into 9 divided by 4 is below, 10 is above, right? I can write 0.4 as 4 below, 10 above, into 1.4, right? Because root 2 is equal to 1.414. That's an irrational number. I'm taking an approximation. Now what I can do is I can write this as 4 6 times, and I can write this as 0.3 0.7, and this can become 3, right? So it becomes 9 3 is 27 over 0.7 into 10 to the minus 2. And then what I can do is I can get rid of this decimal and make 10 above. So I can get 27 over 7 into 10 into 10 to the minus 2. So this becomes 7. I have what? 7 2s are 14, 7 3s are 21, right? Point. So when I have 21, what is left out is 6. Okay. And when I put a point, it becomes 60. So 7 sevens are 49. Okay. And what is 7 6 are? 7 eights are? 7 6 are 42. 7 sevens are, yeah. So we have 56. So 7 eights are 56. And then we have 4 left. That becomes 40. So 7 fives are 35. I think this is enough. So 3.85 into 10 to the power minus 1, right? This becomes 0.385 joules. Okay. So this can be a you again. So this was what I can write here is we got U14 as minus zero point 0.5 joules, and we got U24 as equal to plus 0.38 joules. I'm doing some approximations here. Okay. So the net effect, I can say change in potential energy or delta U, right, would be the sum of these. Why I'm saying change? Because initially when there was a system of three charges, there was some potential energy, and now I brought a new charge. Okay, because of bringing that new charge, their change in potential energy would be the sum of these two, right? And what would this be equal to? This would be equal to minus 0.12 joules, right? So this is what the question was about. So tell the change in potential energy when the new charge is added to the system. I'm not talking about the total potential energy. I'm just talking about the change. So for finding the change, you only need to see. Oh, we missed one more thing. Can you tell me what this one? We missed the Q3 one. Okay. Yeah. Okay. So let's hold this discussion for now and let's calculate that first. Okay. So we need to first find Q3 as well. So the impact or the potential energy change because of the force applied by Q3 on Q4. So let's call that as U34. What would this be equal to? K Q3 Q4 over R34, right? Let's look at the diagram again. So we have the distance as 0.4 and 0.4. That becomes 0.8 meters, right? So then I can write this quickly as 9 into 10 to the power 9 into 2 into 10 to the power minus 6 into minus 4 into 10 to the power minus 6 over the distance, which is nothing but sorry about that. So over the distance, which is nothing but 0.8, right? I'll leave the calculation up to you, but yeah, this would come out to be minus 0.07 joules. Okay. So then now we can come back to what we were discussing before. So the change in potential energy of the entire system of three charges would be equal to the change in potential energy when we were bringing 4 because of charge Q1, then because of charge Q2, and because of charge Q3. And that becomes minus 0.5 plus 0.38 minus 0.07. Okay. So these two, when we added, we got minus 0.12 joules, right? And we had minus 0.07 joules as well. So minus 0.12 joules minus 0.07 joules will give us, can you tell me what is the answer? Minus 0.1. 0.19, right? 0.12 plus 0.17. You can just add 7 with 2. You'll get 0.19. Yeah, I see that you are a bit weak in calculation. 2.7. So 7 plus 2 gives 9, 1, and then 0. So it's 0.19 joules. This is the change in your overall potential energy when the fourth charge came. Okay. So that was about calculation. Okay. Now see, let's try to interpret why is it negative, and if it is negative, what does it mean? Okay. Okay. So what happens is, this is negative because this was a negative charge. Okay. And negative potential energy means that by itself this charge will start getting attracted to this system of charges. Okay. because there is a positive charge which is of high magnitude sitting here. There is a positive charge of again 2 magnitude sitting here, and there is a negative charge also. So this charge would be repelling this charge 4 microcoulomb, but this would be attracting and this would be attracting. So overall, the 4 microcoulomb charge would be attracted to the system, and hence the force that you would be applying would be to stop it from sticking to all these charges together. So rather the force would not be a push, rather you would be applying a pull force to stop it, and then you would be doing a negative work on this charge. Whatever negative work you do gets stored as the potential energy. So here the potential energy is negative. That means you actually reduce the potential energy. You took out some of the potential energy of the system by bringing this new charge. Okay. All right. So yeah, be very particular about what you say. It's not force. Definitely there is a force, but you are doing work against that force, and that works get stored as the potential energy. And we are talking about potential energies and not forces. Okay. So I think this is a good stopping point for today. What do you say?